In 1999, fans lined up at Blockbuster to rent chunky VHS tapes, and early digital culture was just starting to take shape in consumer homes. Amid that dial-up era, NVIDIA released the GeForce 256. It was marketed strictly to PC gamers as the world's first graphics processing unit. At the time, traditional CPUs processed tasks sequentially. They functioned like a brilliant mathematician, solving one complex equation at a time, moving step by step. GPUs solved this bottleneck for gaming by introducing a massively parallel architecture. Instead of processing sequentially, they computed thousands of tiny tasks simultaneously to render complex pixels on a screen. By engineering a chip specifically to push video game graphics, NVIDIA created the exact mathematical engine required to power artificial intelligence. In 2012, researchers realized that training a neural network requires calculating billions of probabilities at the exact same time, a task perfectly aligned with GPU parallelism. A researcher from the University of Toronto used NVIDIA GPUs to feed 1 million images into a neural network called AlexNet. The hardware allowed the model to crush traditional handcrafted software in image recognition. Computers could now learn and adapt from massive datasets. AI moved from a theoretical concept into software capable of superhuman perception. NVIDIA held a piece of hardware uniquely engineered to solve the exact physics constraint that had previously held back deep learning. Today, that architecture has scaled into hardware like the Blackwell B200 GPU, a single chip packing 208 billion transistors. As generative AI models expand to trillions of parameters, they demand entirely new levels of hardware efficiency to operate without crashing. This diagram shows the physical evolution of NVIDIA's Tensor cores. Moving from the older Pascal architecture on the left to the towering Blackwell stack on the right, the new design achieves 32 times greater throughput by natively supporting FP4 operations. The B200 operates as a precision-engineered optimization engine, built specifically to process the massive computing loads of large language models. Raw silicon cannot function without a proprietary software layer, telling it exactly how to schedule and execute the math. This schematic details the Blackwell AI Management Processor, or AMP. It acts as an on-chip context scheduler, offloading CPU work. By managing its own task queue, it drastically reduces latency, instantly prioritizing LLM responses and bypassing traditional hardware bottlenecks. Because NVIDIA's software ecosystem handles this invisible split-second scheduling, switching to a competitor's cheaper chip introduces severe logistical friction. Modern AI systems like Mixture of Experts or DeepSeek R1 now carry hundreds of billions of parameters. They are far too massive to run on any single piece of hardware. NVIDIA addresses this with NVLink, moving 10 terabytes of data per second to fuse 576 GPUs into a single domain. This enables disaggregated serving, where Dynamo software splits the workload. One GPU group processes inputs, while another independently generates outputs. NVIDIA uses proprietary networking to link thousands of processors, turning data centers into one unified supercomputer. Artificial intelligence has moved through distinct phases. It began by perceiving data, evolved into generating text and images, and now performs deep reasoning. We are entering the phase of Agentic AI. The software actively writes code, takes actions, and uses tools to build applications. The next major frontier is physical AI. Platforms like Omniverse and Isaac train digital twins in simulated environments before they interact with the physical world. NVIDIA secured its position by building the silicon, writing the software, and networking the data centers, creating an inescapable full-stack operating system for the future. Subscribe for deeper technical updates on how this architecture continues to scale.